Let me discuss the characteristics of the wave function. This wave function is associated with a particle, and the particle is bound to move within an infinite square well. These wave functions are alternatively odd or even with respect to the center of the potential well. That is, if I look into psi1, that means n equal to 1, then this is center of the well, that is at x equal to a by 2. Right side of x equal to a by 2, the wave function is positive, that is here. Left side of the potential well, the wave function is also positive, which means psi1 is an even function. But if we look into the plot of psi2, with respect to the center of the well, at right side of the well, that is in this region, the wave function is negative, whereas left side of the center of the well, that is between 0 to a by 2, the wave function is positive, which means this wave function with respect to the center of the well is an odd wave function. Similarly, this is an even wave function. Now the next characteristic is how many nodes are there. By nodes, I mean how many times the wave function touches this x-axis. This is my x-axis. I have coincided the x-axis with this floor of the box. I am not considering these 2 points, x equal to 0 and x equal to a, because my boundary condition says that here the wave function is 0. I will count that in between 0 to a, how many times this wave function touches this line of length a. So if I look into psi1, between 0 to a, psi1 does not touches the x-axis at all. So psi1 has no nodes. But if I look into psi2, then psi2 touches this x-axis only once, which means psi2 has only one node. If I look into psi3, it touches at the two places, here and here. So psi2 has two nodes, here and here. So psi3 is having two nodes. Third characteristic is wave functions are mutually orthogonal. Now orthogonal means, orthogonal classically, if we think of the walls of our room, then we can easily see that the three walls, they are perpendicular to each other, which means that the walls of my room are orthogonal to each other. So wave functions are mutually orthogonal means this condition satisfied. And by vector notation, orthogonal means a dot b equal to 0. But here for the wave function, the condition looks like this. For j equal to k, I am going to prove this. So if I want to evaluate this thing within the integration sign, I am starting at this point. I am just substituting with the values of the wave function. Psi is root over 2 by a, sine n pi x by a. My n is j here and n is k here. So for psi j, I need to put sine j pi x by a, and for psi k, I need to put sine k pi x by a dx. But 2 sine a sine b. Trigonometry says that 2 sine a sine b means cos a minus b minus cos a plus b. So here it is. Now it is very easy for me to solve this cosine function. So if I integrate only this, that is integration of 0 to a cosine of j minus k, this is integer, constant, and x is also there, integration is on x. So the result will come as sine of j minus k pi by a, this is constant, x is here, and a by pi j minus k, because we know integration of cos mx dx is equal to sine of mx by m. Similarly, if I want to make integration of this thing, I am getting this, and eventually this will give me 0. This entire thing gives me 0. I have just applied sine a minus b, sine, if I just use this formula, that sine a plus b equal to sine a cos b plus cos a sine b, and sine a minus b equal to sine a cos b minus cos a sine b. So that will give me that this expression should turn up into 0, and this is my equation 10. So I have proved that wave functions are orthogonal. But this thing cannot be applied if I take j equal to k. Here I have taken j not equal to k, but if I take j equal to k, this won't do, because if I put j equal to k, then this term will blow up. Next, I will come to the very important normalization condition. We have already seen the orthogonality, which means their product, if j not equal to k, this integration will be equal to 0. And normalization requires, if j equal to k, this would be equal to 1. Orthogonality we can visualize like sides of our wall. If we coincide them with xyz of the Cartesian coordinate axis, then angle between them, each wall of is 90 degree. That is orthogonality. And together, orthogonality and normalization together can be expressed like equation 11. This is the symbol of Kronecker delta. Kronecker delta has a special property. If j equal to k, then this Kronecker delta becomes 1, and if j not equal to k, then this Kronecker delta will give me 0. Which means if I write orthogonality and normalization condition like this, if I put j equal to k, I will get this equal to 1, and if I put j not equal to k, this would become 0. So this is my orthogonality and normalization condition together. The delta function looks like this. Suppose this is j equal to k, and these are other values of j. This is j axis. Suppose this is this value of j is something other than k. This value of j is something other than k. For j equal to k, this function will survive. Otherwise, it becomes 0. So it is like a spike at j equal to k only. It's just like a spike. Like a spike at j equal to k, otherwise it is 0 here and it is 0 here. This is Kronecker delta function. Another important property the wave function should satisfy is the completeness. By completeness we mean, if I want to write some function fx, then I can write with the help of these wave functions, and this fx can be written completely with the help of this wave function, with just these coefficients are there. These coefficients, something constant like things. So this is a relation of completeness. These wave functions are sufficient, along with these constant values, these coefficients will give me another fx function, and we have already found the expression for psi n, which is root over 2 by a sine n pi x by a. If we put the value of psi n x here, I will get root over 2 by a. This is a constant, so I can be taken outside. A constant means this is independent of n. So I can put it outside this summation sign, and inside the summation sign the quantities that dependent on n only are written. So it is fx equal to root over 2 by a, summation sign, summation goes from n equal to 1 to infinity, cn sine n pi x by a. So infinite number of wave functions will give me another arbitrary function fx. This is equation 13. Now how to evaluate coefficients cn? Because if I do not evaluate coefficient cn, how can we find fx? Because already I have evaluated psi n, just we now need cn's. And later I will show you that what is the significance of these coefficients. In order to evaluate cn, we need to apply a Fourier trick. Orthogonality is a general property of wave function, and this completeness of wave function holds for any potential you encounter. If we have this fx, that is for a given fx, we can find out these coefficients cn, and the Fourier trick is basically it is based on the normalization condition. It is exploiting actually the normalization condition of the whole set psi nx. If psi is written like this, this describes the whole set of the wave function. Just for a change of notation, if I write psi, if psi is complex, then psi star is something which has meaning. So if I write the wave function as psi m star x, and then the given wave function, or the given function rather, fx, then in place of fx we can use this 13 equation number 13. So my equation becomes this, and here I am going to exploit the orthonormality property, that is equation 11 here. So according to equation 11, I can write this entire equation as delta mn. So my this expression becomes sum over n equal to 1 cn delta mn, and as we know that m not equal to n makes the whole thing vanish. So I have to write this as cm, because only n equal to m will survive. So what I get is this coefficient cm, which can be found from the arbitrary function fx and the wave function. Similarly, just a change of notation, I can also find cj from the same relation, and this is equation 14.